Hello students. So today we will be discussing about chemical kinetics, which is one of the most important chapter of chemistry from JEE and NEET point of view. So for study of any chemical reaction, three things are very important. First is the feasibility of the reaction, which we get from thermodynamics. Second is the extent of the reaction, which we determine from equilibrium. And third is the rate of the reaction, which we will be discussing in this chapter, chemical kinetics. So chemical kinetics is a branch of chemistry that studies the rate of the reaction, factors affecting the rate of the reaction, and the mechanism of the reaction. Before moving forward, let's discuss some basic things. First, I will make this statement. As a chemical reaction proceeds, the concentration of reactant decreases and the concentration of product increases. Let's understand this from a very simple example. Suppose we take a vessel of volume V liter where reactant A is getting converted into product B. Now in kinetics, concentration is represented by square bracket. Now concentration of A will be equals to number of moles of A divided by volume of the vessel in liter. This is the concentration of A, that is the reactant. Concentration of B, that is the product, is represented by number of moles of B divided by volume of the vessel. Now, initially, when T is equals to 0, there will be no concentration of the product and the concentration of the reactant will be maximum. Now, as time increases, the number of moles of the reactant will decrease, whereas the number of moles of the product will increase. Now, if the number of moles of the reactant decreases, that means concentration of reactant will decrease, and if the number of moles of product increases, that means the concentration of product will be increased. And that is what it's written in this statement, that as a chemical reaction proceeds, the concentration of the reactant decreases and the concentration of product increases. From this data, we can plot two graphs, concentration versus time graphs. First, concentration versus time graph for reactant. Now, initially the reactant concentration is maximum, and as time increases, the concentration decreases. So we will get a curve like this. For product, the concentration versus time graph will look something like this, because initially the concentration of product is 0, and as the time increases, the concentration of product increases. Now moving forward, students, we will be discussing about two different rates, average rate and instantaneous rate. So average rate is the change in concentration of product or reactant in a given interval of time. So average rate is defined as change in concentration of product or reactant in a given interval of time, and it is denoted as R average is equals to delta C, which is change in concentration, by delta T, that is the time interval. And this species we say plus minus sign, and I will discuss why we are using a plus minus sign. Now let's understand the average rate with a simple example. Let us take a reaction. Suppose A goes to B. At any time T is equals to T1, suppose the concentration of the reactant is C1 and the concentration of product is C3. At another instant of time T2, the concentration of reactant is C2 and the concentration of product is C4. Now, as per the previous discussion, the concentration of reactant decreases, which means that C2 is less than C1, and concentration of product increases, that means C4 is greater than C3. Now, average rate, R average, considering the reactant, will be C2 minus C1, that is final concentration minus initial concentration, divided by T2 minus T1, that is the time interval. Now, C2 is smaller than C1. That means we will get average rate to be negative. Now this is the problem. Can a rate be negative? No, right? Therefore, we have to use a negative sign before. So if we use a negative sign before, then this rate of the reaction ultimately becomes positive. And this negative sign is used in case of reactant, because the concentration of reactant decreases with time, and negative sign indicates that the concentration is decreasing. Now if we write average rate in terms of product, it will be C4 minus C3 divided by T2 minus T1. Now since C4 is greater than C3 and this quantity will be positive, as expected, rate should always be positive. So this is the basically the average rate of the reaction. So if we look it from graphical point of view, suppose this is a graph. This is a curve for a reaction. This is time T1 where concentration is C1, and this is time T2 when concentration is C2. So average rate will be C2 minus C1 by T2 minus T1. Now we will be moving towards instantaneous rate. Now what if I reduce this time interval to very low, that is almost tends to 0. If this time interval is reduced, we will ultimately get something like a point. So the rate at this point will now be called an instantaneous rate. So instantaneous rate is a rate of a reaction, or we can say average rate of the reaction as delta T tends to 0. That means a very short time interval. So it is represented as R instantaneous is equals to limit delta T tends to 0 delta C by delta T, which can be written as dC by dt. Okay, so now this expression I think everyone might be familiar. This is the expression for slope, right? Now if we plot another graph, suppose we are finding the instantaneous rate at this point. Let us draw a tangent at this point. So this expression basically denotes the slope of the tangent at a point in the concentration versus time curve. So this can also be written as tan theta. So this is theta. Now this is the plot for a product, okay, and theta is acute. That means tan theta will be positive. And similarly, one more thing, here also we will follow it by a plus minus sign. Now if we draw the concentration versus time plot of a reactant, then at this point let's find out the instantaneous rate. This will be the tangent and this is the theta. Now theta is an obtuse angle, that means tan theta will be negative. So before this we will use a negative sign such that the rate will become positive. So this is basically the instantaneous rate. This is the average rate and that is the instantaneous rate. So now students, we will be discussing about rate of the reaction from stoichiometry of a chemical reaction. For example, this is a particular chemical reaction where A moles of A and B moles of B reacts to give C moles of C and D moles of D. Now from this equation, how will we determine the rate of the reaction? So rate of the reaction will be equals to minus 1 by A dA by dt minus 1 by B dB by dt 1 by C dC by dt and 1 by d of d by dt. So this is the rate of the reaction from stoichiometry of a chemical reaction. Negative sign, as discussed before, because it is a reactant, the concentration will decrease. One thing is very important to remember, that when you are writing a rate of the reaction from stoichiometry of the reaction, so you have to divide this instantaneous rate by the moles of the reactant or the product that is reacting in this reaction. Now there comes two important type of rate, that is rate of appearance and rate of disappearance. So if it is asked that what is the rate of appearance of C or D, or what is the rate of disappearance of A or B, how you will write it? So rate of appearance of C will be just dC by dt. We don't have to divide it by the stoichiometry or the number of moles of that product, okay? Or rate of appearance, suppose rate of disappearance of suppose A, so it will be just minus dA by dt. So rate of appearance will be dC by dt if we are talking about the product C, and rate of appearance of A will be minus dA by disappearance of A will be minus dA by dt. So this was all about different types of rates of reaction, how we can generalize or how we can represent different rates. Now moving forward, we will be discussing one law which is called law of mass action. So we are going to discuss law of mass action. Law of mass action is totally a theoretical concept which allow us to determine the rate of a reaction. So law of mass action states that rate of a reaction is directly proportional to product of active masses of reactant raised to the power of stoichiometry coefficient. Stoichiometry coefficient. So law of mass action states that rate of a reaction is directly proportional to the product of active masses of the reactant raised to the power of stoichiometry coefficient of the reactants. For example, we have a reaction A plus B. Suppose N1 mole of A and N2 mole of B reacts to give C. So as per the law of mass action, R will be proportional to active mass of A raised to the power N1, active mass of B raised to the power N2. Now what are these active masses? So if these are liquids or aqueous solution, then active masses will be our concentration. Or if the reactants are gaseous, then active masses can be concentration or it can be pressure. For solids, this active mass or pure liquids, this active masses remains constant. So let us suppose these are aqueous reactant. So rate of the reaction will be concentration of A raised to the power N1 and concentration of B raised to the power N2. If we remove the proportionality constant, we will write K times concentration of A to the power N1, concentration of B to the power N2. So this we get from, this is the rate law we can say that we get from law of mass action. But this might not give us the correct result and might not match with the experimental value. So we need some modification in this reaction. So we will move forward. So for a particular reaction, the rate of the reaction can be determined theoretically, that we just discussed, by law of mass action, or experimentally. Now there are two cases that will arise, that is, theoretical rate might be equals to the experimental rate, or theoretical rate will not be equals to the experimental rate. So to get a generalized rate equation which will satisfy all the time that theoretical and experimental rate remains equal, we need a different rate law, and that is given as, for example, a reactant A plus B goes to C, then rate will be proportional to concentration of A raised to the power x into concentration of B raised to the power y. So R, or the rate, will be equals to K times concentration of A to the power x, concentration of B to the power y. Now you might be wondering what is x and y. So don't get confused, x and y is not the stoichiometric coefficient of the reactant. X and y has a different naming in chemical kinetics. We call it as order of the reaction. X and y both are order. That is, x is the order with respect to A and y is the order with respect to B. And if we are asked to find what is the order of the reaction, then order of the reaction will be summation of x plus y, that is order with respect to reactant A and order with respect to reactant B. So this is the generalized rate equation that we will be using throughout this chapter. Now let's conclude this lecture with a question from rate of the reaction. What type of question can arise? For example, let's take example of this question. For a reaction N2 plus 3H2 goes to twice NH3, rate of disappearance of H2 is 0.5 mole per liter per second. What is the rate of the reaction? Now we will apply all the concept that we learned in this video. First, since the reaction is given, we will write the rate based on the stoichiometry. So rate will be equals to d of concentration of N2 by dt with a negative sign, or minus 1 by 3 d of H2 by dt, or it will be half d of NH3 by dt. Now in the question it is given that rate of disappearance of H2 is 0.5 mole per liter per second. That means d of H2 by dt is given as 0.5 mole per liter per second. Okay, so basically this we have been given and we are asked to find the rate of the reaction. So rate of the reaction will be minus 1 by 3 d of H2 by dt. Now minus d of H2 by dt is 0.5 mole per liter. That means it will be 0.5 mole per liter per second divided by 3. This will be the rate of the reaction. Suppose in this question they might also ask what is the rate of appearance of ammonia. From this particular equation we can determine everything. Since d of H2 by dt is given and this is equals to this, if we take this 3 here, then it will become 3 by 2, and since minus dH2 by dt is given, then 3 by 2 dNH3 by dt, or if we take this 2 here, then we can get the rate of appearance of ammonia. So rate of appearance of ammonia will be 2 by 3 rate of disappearance of H2. So we will stop here. So today we have learned about different rates of the reaction, how we can calculate the rate of a chemical reaction, how we can calculate appearance rate of appearance of a product, rate of disappearance of the reactant. We have seen average rate, instantaneous rate, how we can determine this rate from graphs, and we have also seen how concentration of product and concentration of reactant changes with time, both graphically. So this was all about rate of the reaction.